Baik, terima kasih kepada Bapak dan Ibu yang telah mematikan mikrofon untuk kenyamanan acara webinar pada pagi hari ini. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera untuk kita semua. Our respected Mr. Aksai Sawan, as Senior Application Engineer, Solution Engineering Bentley System. Our respected Jamie Howe, as Product Sales Engineer Bentley Systems. Yang saya hormati Bapak Junius Halawa, as Application Engineer Solution Engineering Bentley Systems. Dan yang saya sangat hormati dan muliakan Bapak dan Ibu peserta webinar baik dari PDAM, kontraktor, dan konsultan. Alhamdulillahirrahmanirrahim. Kita panjatkan puji dan syukur kehadirat Allah Subhanahu wa Ta'ala. Pada hari ini, acara webinar dapat kita selenggarakan. Terima kasih yang sebesar-besarnya kami haturkan kepada Bapak dan Ibu yang masih tetap bersama kami sampai di acara webinar sesi 3 hari ini. Bertemu kembali bersama saya, Nesi, dari PT Kurnia Handasa Nevada, Bentley Channel Partner Indonesia, Authorized Partner untuk penjualan software Bentley di Indonesia. Bentley Systems berpusat di Amerika, berfokus pada pengembangan engineering software, mulai dari perencanaan, desain, konstruksi, dan pengelolaan infrastruktur. Salah satu bidang yang menjadi perhatian utama Bentley Systems saat ini adalah sumber daya air. Tema besar 3 series webinar kita adalah Smart Water Loss Management and 24 Hours 7 Days Supply Resilience. Tema dari sesi ketiga webinar kita hari ini adalah Transitioning to 24 Hours 7 Days Continuous Water Supply, Risk Mitigation, and Energy Optimization. Pada sesi ini, kita akan membahas gambaran umum sektor dan kondisi sistem yang ada saat ini, evaluasi sistem existing, transisi menuju sistem pasokan air 24 jam selama 7 hari, manajemen tekanan menggunakan optimasi pompa dan valve, dan analisis transient, water hammer, dan metode mitigasinya. Hadirin yang terhormat, kita akan memasuki sesi materi pertama yang akan dibawakan oleh Jamie Howe yang akan memaparkan pengenalan open flows dan success story di Indonesia. Hi Jamie.
Hi Bu, good morning.
Yeah, I'll now hand it over to you.
All right, thank you so much Bu. So
Thank
let me know if
you.
you can see my screen.
Yeah,
I
we
think
can
it's
see
okay.
it.
All right, thank you. So once again, thank you Bu Nasi again for organizing this event. Thank you Akshay and Juniors for being here with us and supporting this as well. And thank you all of you for joining us today. We hope you find today's topic insightful and the whole webinar series helpful in your upcoming or ongoing projects. So welcome back again to our webinar series as introduced by Bu Nessie, Smart Water Management and 24 hours, 7 days a week supply resilience. And just a quick recap, in part 1, we focus on reducing losses, looking at how utility and water bodies can reduce non-revenue water through leakage detection and pressure management. And in part 2, we explored on how to move from static hydraulic models to systems with real-time visibility and control. And this will enable more proactive and informed network operations. And now today, we will move into part 3, our final session of this webinar series, where we will build on this foundation from part 1 and 2, looking at how utilities or water bodies can change or improve from intermittent supply towards a reliable and more sustainable water supply 24 hours a day, 7 days a week. And in many regions today, as you can see from this slide here, achieving continuous water supply is still a major challenge. And intermittent supply is very common and often due to pressure fluctuations and system inefficiencies. So at the same time, high levels of non-revenue water, it will reduce the amount of water that is actually available for distribution. And with growing demand, water bodies or agencies are also under pressure to do more with limited resources. So the challenge here is not just about producing the water supply, but also delivering it more reliably and more consistently and efficiently as well. And so how do we move towards a continuous supply? It starts with these few questions shown here. Whether your system can it deliver water consistently? Are the pressure zones properly managed? And is the network optimized for reliability? And this is where we shift from intermittent supply to a more stable and continuous system. So if we look across the three parts, like what we mentioned just now, part one was on identifying and reducing the losses. Part two was on real-time operational intelligence. And now in part three, we bring all this together to scale toward a continuous supply. Because by achieving continuous supply, it is not just one step, it's a result of continuous and cumulative improvement in your whole network or system. And let's take a look here at this example from Indonesia. This is by PT Wika Tirta Jaya Jati Luhur. In this project, the focus was on delivering clean water across a growing region in Jakarta, Bekasi, and Karawang corridor. There was also over-reliance on groundwater or as a source of water, which poses environmental risks. So for this, they need a large scale and a reliable water distribution system. And by doing that, an 80-kilometer transmission system was then developed to support this large-scale distribution. And using OpenFlow's water and digital workflows, they were able to carry out all detailed assessment like pipeline sizing, assessing the pressure zones, and also pump efficiencies. Today, the system now delivers approximately 4,750 liters per second to over or more than 380,000 residents in that area. So by optimizing the network design, the project achieved faster delivery timelines and also reduced reliance on groundwater. So this case study here shows how infrastructure and system planning come together to enable a reliable water supply at a large scale. And so to support this kind of system and planning optimization, water bodies or utilities need to have the ability to model and to simulate and evaluate the different scenarios in the network or in the system. So this is where OpenFlows plays a key role in your hydraulic model. OpenFlows not only support water distribution network, it also supports wastewater and stormwater network systems as well. So it will help all of you engineers and water bodies and agencies to test different kind of strategies, understand the system behavior better, and also make more informed decisions before any implementation is done. So the three core OpenFlow solutions, the water, the sewer, and the storm, are also complemented by the OpenFlow's hydraulic toolset and OpenFlow's flood. The hydraulic toolset is for calculation of specific components, and OpenFlow's flood is for advanced flood risk analysis and assessment purpose. And the tiers, we have also shown this in earlier parts where it mainly defines your based on your model capacity and capability of or extent or requirement of your assessment, such as the number of pipes or elements. So you can choose a setup that fits the scale of your network or the system that you want to study. So each tier use the same modeling environment and methodology, just with increasing capability. As we can see here, for OpenFlow's water, this is our focus for today. And this slide here is just a very simplified comparison that shows how each tier supports different levels of your assessment, depending on the complexity of your system and also the type of study that you want to perform. So from very basic network modeling to more advanced capabilities from the left to the right, like transient analysis and optimization, the higher tiers will allow you to evaluate all this in your system in greater detail and also allow you to make a more informed and better decision on your system. So this is very particularly or very valuable when the planning for system improvements and when you want to move towards a more continuous water supply system. And we run through quickly on Virtuoso Practitioner License. So Virtuoso is our e-commerce platform license that you can purchase at an affordable price, and it comes bundled with trainings. So how does it work? It is a very flexible subscription because it can be purchased by any entity, be it if you are from a large organization or from a small organization, or even if you're just an individual who wants to do your own assessment or doing freelance kind of projects. And it is also flexible in terms of duration of your subscription. It's just a 12-month subscription. So if you are doing projects for a short duration, let's say 1, 2 years or 3 years, 4 years, you can always subscribe to the solution that you want throughout the duration that you want to use the license. And after your scope of work or your design requirement has ended, then you do not need to continue the subscription anymore. And also the keys or the tokens for you to redeem free customizable training. This comes, there are keys that comes bundled with a license. We can show you in this example here. For example, if you purchase an OpenFlow solution from Virtuoso for Virtuoso subscription, it comes bundled with keys like what we've mentioned just now. So with all these keys, you can redeem or unlock different types of free trainings that is available. There are some on-demand or recorded trainings where you can watch it at your own time, at your convenience for a period of 90 days. And there are also tailor-made trainings and also mentoring services which are customizable. The contents are customizable to your team's project or design requirements. You can further discuss this with our technical expert after the purchase of your software so that they can work out a module or a session that works for your team. And the number of keys, it varies depending on the product tier that you purchase. So since today's focus is on water, we are just going to look into the water solution, OpenFlow's water. The essentials and standard tiers, they come with 1 key per license, and the advanced and ultimate tiers, they come with 2 keys per license. 1 key is almost 2 hours of free training that you can redeem. So in summary, Virtuoso is a practitioner license with named user. So you can reassign the license if required. And it is a yearly investment without any additional maintenance fee. So with this, you can have better control over your yearly software cost for your project. And throughout your whole active subscription period, you can have access to free technical support assistance, free software updates and upgrades, and also expert services using keys. And if you have any queries, either on OpenFlow's solution or on Virtuoso subscription license, feel free to reach out to Bu Nesi or PT Kurnia Handasa Nevada. They are one of our channel partners here in Indonesia, and we are happy to work together with them to assist you on any concerns that you may have. So that's all from my end right now. Thank you so much. I'll hand over back to you, Bu Nesi. Thank you.
Thank you, Jamie, for the brief introduction. Hadirin yang terhormat, kita akan memasuki our main session delivered by our keynote speaker, Mr. Akshay Sawan, as Senior Application Engineer, Solution Engineering, Bentley Systems. Hi, Akshay.
Hello, Bu Nesi.
Yeah, the floor is yours. Thank you.
Thank you. Thank you so much, Bu Nesi, for arranging this webinar series. Thank you, Jamie, for the wonderful introduction. Let me share my screen and just confirm once it is visible.
Yes, it is.
All right, so let's move to the third part of this series. I know you have attended the first 2 parts. Some of you may not have attended, can go and watch the recordings of it. Some part what we will be discussing today you may find it repeated. Okay. Also, if I'm going very fast, please let me know. I will slow down a bit. So let's discuss. First, let's discuss Indonesia, the current challenges what the water supply systems or the utilities are facing, and then we'll move on to the solutions. So this is the agenda that we will be following. First, we will discuss the sector, then we'll talk somewhat about the design parameters. Then we'll talk about open flows water, how we can convert an intermittent system into a 24/7 system. Then we'll talk about extended period simulation, uh, variable frequency drives, pump controls, valve controls, and finally we'll talk about transient analysis. And also we will be talking about the energy optimization, how you can use open flows water for the same. All right, so let's talk about the sector, that is the water sector. When we talk about institutional structure and service delivery model for Indonesia, it is highly decentralized. Urban water supply, basically, it is mostly decentralized, managed by approximately 380 regional utilities called the PDAMs, and I have been fortunate to visit some of them uh, across multiple cities in Indonesia. National ministry roles, multiple ministries share the oversight. Public work supports infrastructure, home affairs governs the administration, and health sets the quality standards. You can also correct me if somewhere I'm going wrong. Whatever information I have from the internet and whatever visits that previously I've done. And the performance variation challenge, that is the main thing. PDM utility performance varies widely, with some efficient, and some of them are facing technical or financial or political challenges as well. Right. So we will be discussing mostly about the challenges. When we talk about sources, again, it is diverse sources. Indonesia relies on surface water sources like river and reservoir, and many cities, including Jakarta, heavily relies on groundwater, right? And the next challenge, what we can say, is intermittent supply. Most of the utilities are not functioning 24/7. It is intermittent supply. And because of this, it is low pressure, storage limit, high leakage rates, and so on. When we talk about treatment and usage, water treatment again varies. Utility treat water to the standards, but consumers often boil and buy bottled water for consuming purpose, drinking purpose, and resource and sustainability risk, uneven water distribution, obviously, pollution, groundwater over extraction, right? So all these are challenges which needs to be overcome. When we talk about coverage and performance at the national level, uh, the service coverage and access, when we talk about the overall water supply system, it is 94% population has got, sorry, 94% have access to improved water sources, but only 20% have piped water connection nationwide. Means 94% population has got the access to water, but 20% have got piped supply up to their household, right? Or maybe it is kind of groundwater extraction that is dominant compared to the water supply system, right? So mostly people don't opt for the piped water supply system. Instead of that, they use their own groundwater sources to consume the water. Uh, when we talk about equity and quality, households without pipe connections pay more, face higher risk of high health risk from inconsistent water quality. It all depends on the quality of the groundwater, right? Uh, and the sewerage coverage is as low as 2% for urban population, which is actually very, very low. This also needs to go up. And when we talk about government expansion goals, there is an ambitious target of universal piped water access by 2045, right? So let's see how it goes. There are around 20 years And in that, we need to cover the whole Indonesia with piped water supply systems. When we talk about the common challenges in urban area, the first challenge, that is high non-revenue water. I think except Singapore, everybody in the world faces this. Singapore has got a very good system. Some of the utilities across the globe have got, I mean, only few of them, handful of them have achieved good NRW targets, but many of them face issues of this non-revenue water. Many places the percentage is above 50%. Okay, so this is a worldwide issue and everybody is trying to work on it. When we talk about intermittent water supply, uh, water supply is often intermittent with low pressure, failing to reach higher buildings effectively. Again, aging infrastructure is also an issue. When we talk about cities like which have been there since maybe so many years, some of the pipelines are now old, and we means there is kind of replacement required because of frequent breakdowns, other maintenance issues, right? So that is kind of aging infrastructure. And the water quality concerns, pollution and inadequate treatment lead to unsafe tap water, undermining public trust in safety. So these are all the challenges. When we talk city-wise, let's talk about first Jakarta, that's the capital. 64% of Jakarta's population has piped water access. Uh, Again, Jakarta has its own problems. Only 64% of the population is covered. What is the rest of the population doing? Or there are so many commercial establishments in Jakarta. So what are these establishments doing? They're extracting water at a very high rate. Uh, Groundwater extraction is okay, but if the groundwater extraction rate is very high compared to the recharge rate, it is a problem. A city like Jakarta, which is so like uh, so big, you're simply extracting water at a very high rate, and if the water is not recharging, I know the rainfall amount is very high in Jakarta and overall Indonesia, but still the groundwater recharging is very important, and that is not happening. And you can see there is subsidence also happening every year. I forgot the rate of subsidence, but yeah, because of subsidence, again, Jakarta is facing the flooding issue, coastal flooding majorly. So all these issues are there. Only one thing can improve that is means imagine uh, uh, this thing, because of water supply systems. If 100% population gets connected with a piped service connection, uh, you will not have floods, right? So to understand means maybe a common man won't be able to understand, but as hydraulic engineers, as engineers, like you are working in the field, you know this issue, why Jakarta is facing this flooding issue every year. Mostly when we talk about the coastal flooding, it is due to the subsidence, right? So yeah, all these challenges are there. When we talk about Surabaya, again, I was fortunate enough to visit PDAM Surabaya, and let me tell you one thing, that the model that I saw, the water gems model that was prepared by PDAM Surabaya, it's the largest model that I have seen ever in my life. In past 8 years, I have seen that is the largest model, largest as in kilometer terms, it is around 6,700 kilometers, and still it may increase further with more details. And it has got so many scenarios as well in the model. So it is the biggest model that I have seen. And uh, having said that, software has helped a lot uh, to the PDAM over there, and you can see because of that. the coverage, basically the PDM Surabaya has got a very good coverage of like it has everybody has got piped service connection. Only challenge is the new areas that are popping up, the new urban area or the new urban growth that is happening around Surabaya. So uh, the utility is trying to match that, right? And I think software is helping them in that part. When we talk about Bangdung, service coverage and challenges, urban core has moderate water coverage, peripheral areas face frequent service interruptions and low level. Again, the NRW is high in this particular um, city, and there are certain constraints to the improvement of the utility. Uh, when we talk about Malang, uh, it has got again good service coverage. It is again near Surabaya, right? So it is again having a very good service coverage. It has got continuous supply. It demonstrates strong utility performance. And talking about NRW, the city reduced its NRW to about 16%, which is very, very good. Okay. And it is well below the national average. Talking about infrastructure and management reforms, systematic infrastructure rehabilitation and modern management practices enabled Malang's water efficiency gains. So this can be a case study for all the other utilities uh, around the around the country. Okay. Now, when we move forward, let's talk about solutions. And as I said, some of them may be repetitive. The need. Let's talk about the need first and the challenges. Uh, so first thing is intermittent supply. With intermittent supply, you have to send the same amount of water in few hours. Means whatever a person has to consume in 24 hours, the same amount of water you have to now send or deliver it in small amount of time, which increases the pressure on the system, right? And that brings down the performance of the system. So what does intermittent supply corresponds to? It corresponds to low pressure and inequality. What happens is the people staying near the source of water, suppose it's a tank from where the water is going to be supplied, what happens is it's a behavioral change that needs to be coming into the citizens. What happens is somebody staying near the tank, the water is supplied, the water reaches to the consumers first, who stay near the tank. They will start filling up their own tanks, own reservoirs, whatever they have in their homes. This is a general thing that occurs everywhere. Okay. Now imagine somebody having 24 by 7 supply of water. They won't need to store water in their own reservoirs, in their own tanks, right? So that changes the behavior. So that is one of the prominent thing that comes with intermittent supply. The behavior of a consumer. Okay. Uh, when we talk about 24 by 7 supply, it increases the pressure exposure, risk of leakage, burst, and failures. So this comes with both intermittent supply as well as 24 by 7 supply, but it comes more with intermittent supply because the pump starts and stops many more times than 24 by 7 supply system. Okay. And everything is data based. Now everything is data. Every point or every pressure date point is a data. So if you have more data, you can take more better decisions. Okay. And why we need digital modeling? I think you can study the Surabaya case. They have such a large network, and that helps them to take further actions, that how they can improvise further. So why digital modeling? Avoid your trials and errors in the field. Okay. lot of time is saved by looking at the model itself. You need not send your team unnecessarily into the field. You can just check all the data first in the models, and then you can take an improved decision to send your team and basically spend man hours on the field. Uh, you can simulate the real network behavior. I think in the second webinar, we have discussed the digital twin. When we talk about scenarios, like I mentioned that Surabaya model, there were so many scenarios, more than 50, I think. I don't remember exactly, but uh, the, the 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 number of scenarios were so many of them. So there is no limit to create scenarios, right? So you can, as per your operational requirements, you can go on creating scenarios, test them on the model, and then implement it on the ground. Or suppose if you want to install new valves on the ground, any type of valve, you just first check those valves in the model and then take a decision to purchase and then finally install it on the ground. So you can also predict failures before implementation. So any failure point you can predict, and you can save your system from any kind of catastrophe, right? So this is the need of the modeling. Let's talk about the first step, that is calibrating a model. So suppose a system is already running. Now you want to test your system, or you want to check where is the NRW or where are the leakages. Okay, this is just one point. There are so many other points, like you want to test the system for how it's for any performance indices. So indexes. So suppose you want to check how many number of consumers are getting affected because of throttling one valve. This is one condition. You want to check the performance of the pumps. This is another condition. Similarly, NRW is one of the conditions. So you want to check that thing. So how you can do it, how you can do the assessment. Let's check with the help of this video. Now, the points that you see, this is observed pressure data. Okay, there are so many junctions, but the highlighted junctions are the junctions where you are getting the pressure data. Okay, so this is the observed data. Now, this is the tank from where the water is supplied to the consumers. And this is the model that is giving the output. Like this should be the flow. Now you integrate the observed data with it. Okay, you add the observed data. Now a table of observed data has been added. Now you can see the difference between the observed data and the actual, I mean, the actual data and the model data. So there is something called as Darwin calibrator, in which you can add all this observed data. Now this is field data. Every 15 minutes, a field data has been collected for all those points that you saw. So there are pressure transmitters and there is a flow meter at the start of the network. So you add all of that observed data in this, then you will decide the number of trials you want for coming to a conclusion. So here 10,000 trials have been taken, okay, to run this calibrator. And with help of that, you will see there is something called as emitter coefficient. So emitter coefficient decides, or basically it is that property of a junction which will affect the pressure or affect the demand in that particular, not the demand, but the pressure in that particular junction. Okay, so if we multiply the pressure by zero 0.5, that is the overall effect. So that is what 50% of pressure is affected in this particular junction, or 17% of pressure is affected in junction 445. So this is the result that you get. So 1, 2, 3, 4, 5, 6. So these are the 6 junctions where the pressures are getting affected. And how did we get this? We got this from the observed data. Then we run that observed data in Darwin Calibrator. Okay, this is the here you need to compute this, and after that you will get these results. Now you can mark these results on the model. You can visualize that thing. You can run more trials as well if you want. You can export that as a scenario. Okay. Once you do that, you can go in that scenario and you can again create an element symbology for emitter coefficients. Now you can see these are the points where there is probable leakage. Now, except for the, I mean, instead of sending your team across the project area, now you have shortlisted these 6 points where there is probable leakage. Okay, so you can send your team to these locations and then they can find out those leakages, move to the next point, find out the leakages, move to the next point. So what is happening is you are saving so much amount of time of your field team. Okay, and also maybe you can save man hours with reducing the team members. Uh, Once you do that, you can again check with the observed data. Now you can see over here, this is the observed data that we have run. You run the model again, and now it will match with your observed data. So this is one of the thing that you can do for system assessment. This is, we call it as leakage detection tool that is done with help of Darwin Calibrator. Okay, once you do this, all of this for your intermittent supply system, it can be for intermittent, it can be for 24/7. For I mean, as per your requirement, you can do that. Now, moving to the next point is you switch to 24/7. Okay, that the first step that you saw, that was system assessment that you can do for your intermittent supply system. Now, when we talk about 24/7 system, again, let's see how it works. So this is a scenario of intermittent supply. This is the this is actually under construction. This is the source with two pumps in parallel, and this is the intermittent uh, supply. Now you can see over here, this is the hydraulic pattern that the intermittent supply is going to follow. There is no supply for so many hours, then there is supply for around 4 hours in the morning, then again there is no supply at all, again in the night there is around 4 hours of supply. So you can run these types of patterns and you can observe the data. Okay, now this is the time browser. You can see the dark nodes that you see are having no water at that point of time. Okay, some of the network is still having water. Why? Because of the service reservoir. The capacity of service reservoir is large. That is why it is having water. But at certain places, you can see sometimes the water is getting overflown, sometimes the water is getting emptied. I mean, the tank is getting emptied. Now I have changed the scenario to 24/7 pattern. Now you can see there are no dark nodes. That means there is pressure every time. This is the pattern that has been given for 24/7 system. Again, let us check this particular tank for its uh, capacity graph. So you can see now there is no uh, overflowing or there is no emptying of that tank. So you have now switched to 24/7. Now again, one more point over here, that when we were in the uh, intermittent scenario, this part of the network was not present. When we switch to 24/7, this part of the network has been added uh, uh, into the main model. So such types of scenarios you can go on creating. This is kind of a new extension for this particular project. Okay. Now let's talk about the next step, that is pressure management. And again, there are so many ways to do the pressure management. One of which we will discuss, that is use of variable frequency drives. Somewhere it is also called as variable speed drives, okay, which are very, very useful when it comes to uh, pressure management. Now, in the same model, there is a VFD pump. Now, what is the role of this pump? I'll first explain. So this is a tank over here, and then there is a pump. So the tank, which is already there, it's a elevated service reservoir, but the requirement of the pressure at the end point is around 25 meters H2O pressure. And this tank height is not that much. The tank height is small. It's around 15 meters height. So the head is not available. So there is a booster pump installed just in front of the tank, which is helping to improve the pressures in the downstream. And this pump is a VFD pump. Okay, depending upon the supply, uh, uh, the pump motor changes. I mean, the speed of the motor changes, and the pump performance remains constant, or the head requirement remains constant. So, how we have done that? Let us see that. So you can observe the levels over here for the tank, and this is the pump. It has been defined as a variable speed drive pump. Okay, it is based on the target head. You can also add a fixed flow or pattern based flow, and the hydraulic grade of this particular junction. This junction has been associated with the performance of this pump. Okay. And let me also show you the pump definition. It's 11 meters of head. So it is just adding 11 meters of head into the system. Now let's trace whatever is in the downstream of this pump. Let's check the junction pressures. You can observe the pressures against the time browser. You can see how the pressures are changing, but those pressures are not fluctuating very much. It is just some points difference. Okay, that is the beauty of any VFD system in place. Right, so this was the elevation of the tank, 249. Upon that, we are adding 11 meters of head that is acting as a booster pump. So this is one of the way to manage your pressures. Now talking about step 4, comparing of scenarios. So you create multiple scenarios. I told about Surabaya. They have more than 50 scenarios. So you can also have multiple scenarios in the same model. In this model right now, see, you can see intermittent scenario is on. Okay, and you can see lightly there is some part of the network which is not active in this particular model or this particular scenario. If here also there is some kind of network, I think because of the background it may not be visible to you, but yeah, there is some part of the network over here and some part of the network over here which is currently inactive, but in another scenario it will be sorry. Okay, so in another scenario, it will be active. Now, how you can compare scenarios or what type of data you can compare? So there is something called as, in the review tab, there is something called as scenario comparison. Okay. So you select any scenarios. Now we are comparing a 24 VFD scenario with a intermittent scenario. Just press OK and it will showcase you which properties are changing. So first of all, it is the topology which is changing because some part of the network is not present, some part of the network is present, right? You just press this compute button and then you can check one by one. So here you can see these are the junctions which are active in this particular scenario, are not active in this scenario. Okay, so these are, yeah, so these are the junctions. which are inactive. Similarly, you can check pump, pipes, tanks, all the elements which are present or not present in any of the scenarios. Next, what you can check is yeah, so this is the tank which is not present in intermittent. It is still under construction, so it is not present in the intermittent supply system. And this is the physical property. So which physical properties are changing, you can check for the pumps, pipe, tank, whatever elements are present, you can check which diameters are changing in the scenarios, what material is changing, whatever change is there in between the scenarios, you can check. And uh, mostly in this particular model, the demand has changed. Now, VFD has been run for in ultimate case or another demand, I can say, another horizon, and intermittent system was run for another horizon. Okay, so there is change in all the junctions or the demand of all the junctions. So that is how you can compare the scenarios. You can also create graphs, overlapping graphs. Now, I'll just pause this video and explain a bit. So you can see there are two graphs, okay, of the same tank, and it is showcasing the percentage full level. The first blue colored graph that you see, the water level over here, it is reaching 100%. That means it is now overflowing. Okay, it cannot accommodate more water inside it. After around 6 a.m., you can see when the consumer is consuming water, uh, the level of the I mean the tank water level is going down, and it is also reaching zero. That means it is getting emptied. And if you remember the previous video, there were some dark points or dark nodes which were indicating there is no pressure. That means there is no water. And it is the downstream of this particular tank in this particular time. Okay. And this also this particular time. So you can check all of this data. You can assess your models with all of such types of analysis. Now, this is the same tank in another scenario, that is 24/7 scenario. You can see how the water level it drops down a bit, again it increases. So here actually the controls are given such that the pump is not working in these 2 hours, and again the pump starts working once the consumption increases during the morning time. The water level recedes, and again in the evening it increases a bit, again at the night it decreases, and so on. So this is only for 24 hours, but you can keep on running this until you find equilibrium for your model. Okay, so such type of analysis you can do, such type of comparison. Now here, okay, this is another comparison, flow of the pipe. Now, when we talk about the flow of the pipe, you can see the red, again, it's a 24/7 system. The blue is a intermittent supply system. Now you can see the flow is very high in the intermittent supply. Why? Because as I mentioned in the beginning, you have to deliver the same amount of water to your consumer in very less time. So in that less time, you have to deliver more amount of water, and that stresses the systems, stresses the pipes. Okay, so such types of studies you can do. Let's move to the next point, that is transient analysis. Now, you saw there are so many pumps in this particular model. You may also have so many pumps. Even if you don't have pumps in the distribution side, you will have pumps in the transmission side, and we need to do something called as transient analysis. If we don't do that, there are chances of pipeline burst, and sometimes if the pipe is of a bigger diameter with a heavy demand, demand as in the flow, heavy flow, uh, it can also be catastrophic sometimes, right? So let me run this video. Now, this is not a typical example of a distribution network. This is basically a transmission network. Now you can create multiple graphs to study how the transient pressures are working. Okay, again, there are two scenarios in this particular graph. Uh, there are two. First, let's talk about the air vapor volume. You can see there is a flat line and there is a pink line which is having some hump. So when we talk about the flat line, that is with the protection device, and this hump that you see or the vapor volume that you see, this is the vapor volume, like it is reaching around 500 liters of air volume, vapor volume. So this is one without protection. Okay, similarly, if you see over here, the green line indicates the hydraulic grid, which is dropping because of some condition that we have simulated. In this case, we have simulated the power failure condition where the pump is tripping or pump is shutting down. Similarly, you can create multiple conditions of valve operations. Suppose a valve is throttling for 15 minutes, 10 minutes, uh, any kind of that condition, you can simulate and check the transient pressures. These pressures are very important because a wave travels with the sound speed inside the pipe, and that causes a huge trouble. The water also kind of flows in with the wave. The water also like travels with a very high speed. Okay, so you can see there is down surge or a negative pressure. Now this negative pressure can collapse your pipe and road cave-ins may get formed. Okay, and if it is high pressure, as we see over here, it's not that high, but suppose it is very high. Okay, in some cases it goes about 300 meters of pressure or 400 meters of pressure. uh, that time you need to check or you need to give some protection device for upsurge as well, that will protect the system from bursting of pipelines. Okay, so this is the graph. These are the graphs that you can study and you can analyze where you can install the pipes. Sorry, install the protection devices. Again, let me explain with the same thing with help of another set of graphs. These are three different scenarios. The first one is without protection. Second one is with a hydropneumatic tank, and third one is with a surge tank. Okay, this graph that you see, the bottom line that you see is the elevation profile. This is actually green in color. It may not be visible that prominently in the video, but this is green color, which explains the elevation profile of the alignment. This is a black line, which is the normal hydraulic grade when everything is fine, system is running fine. This will be the hydraulic grade. But once there is some issue in the system, suppose again in this case it is pump failure condition, that is power failure condition, when all the pumps are tripping at the same time, you can see a down surge, continuous down surge line. Okay, this blue line is a down surge line, and this is an upsurge line. These are air vapor volume. Uh, Again, in the second scenario, there is a hydropneumatic tank. It's the same alignment. Now, this line that you see, the alignment line is at the bottom, and the downsurge line is actually above. That means there is no negative pressure in the system. So there won't be any collapse of the pipe. Okay. Then the upsurge, it is still there, means there is some kind of upsurge still there in the system, but you need to check the value of that. It is only 30 meters of pressure. If you see over here, this is around 55, this is around 85. So it's just 30 meters of pressure, which can be sustained by the pipe. So you need not give any protection device for upsurge. But suppose this was like 300 meters of pressure or 400 meters of pressure, then definitely you would have proposed some other protection devices. So what are the protection devices that are available in the software? It is hydropneumatic tank. We also call it air vessel. Some places it is called as surge vessel. Then when we talk about one-way surge tank, two-way surge tank, then there are different types of air wells that you can install. Rupture disc. You can also install different types of surge valves. So all these is available to protect your system. And after that, I'll just conclude with this part. I mean, I'll discuss this part and then I'll conclude and stop for the questions. So yeah, again, whenever we talk about 24/7 system, or for that matter, intermittent system, the most important point is energy consumption. Every contractor that is running, or every utility that is running the system, gets a very big energy charges cost, right? So they spend a lot in that. So how you can optimize any system? Let me run this video. So this is a source of water. Then there are 4 different pumps, 2 big pumps, 2 small pumps. And this is the whole network. There is a tank at the end. And let me run this quickly. So again, let's go into the summer scenario. These are some controls given that when a pump will turn on and turn off. Like if the tank level is below 99.06, big pump 1 will start. Okay, if it is above 103.33, big pump 1 will stop, and so on. There are so many conditions that have been given to run the model. Once you run the model, you just let me just explain this. Now this is the hydraulic grid. It is starting at around 102. Once it falls at this level, you can see the other pump also starting. So this is the flow of the pump 1, big pump 1. It is continuously running. The blue color is that one, and the red colored, you can see it is only starting at some parts of the whole run. Over here, if you see, both the pumps are shutting down at this point of time because the hydraulic grid is going above 103 or something. Okay, so this is one scenario. Then there is another winter scenario where only one pump is functioning continuously because the hydraulic grid is not dropping that much. Once you do all of that, there is something called as energy cost scenario, energy cost computation. You go into that options, you define your rates. It can be block rate, it can be a constant rate, it can be a rate including the peak demand charges as well, if you have any kind of that. Now here it is 8.7 rupees, Indian rupees. In your systems, it will be Indonesian currency per kilowatt. Okay. And you can also add the carbon emission data per kilowatt, and then you can check the results. Okay. You can compare the scenarios. You can check all of these details like the total energy consumed, total energy cost, the storage cost of energy, the daily energy cost, the volume of water that was passed through the pumps, unit energy use, unit energy cost, peak energy demand. Here it is 0 because in this particular case, it is only the block rate that has been given. Then the carbon emission and so on. So run duration also, here it is 24 hours. For your case, it may be some intermittent hours as well. So you just test your system with multiple scenarios, and whichever is the most efficient scenario, you can check from here and go for its operations or replicate that in your operations. Okay, so I think with that I will stop for questions. over to you, Jamie.
Thank you, Akshay. So, thank you for the presentation. So, Bu Nasi, would you like to introduce our?
Yeah, thank you very much, Aksai. We really appreciate the deep knowledge you have shared with us today. Bapak dan Ibu, sekarang kita akan memasuki sesi tanya jawab yang akan dipandu oleh Bapak Junius Halawa selaku Application Engineer Solution Engineering Bentley. Kepada Pak Junius, dipersilahkan untuk memandu sesi Q&A.
Terima kasih Ibu Nesi. Bapak Ibu sekalian, saat ini kita buka waktu untuk bisa bertanya secara langsung terhadap presentasi yang sudah disampaikan oleh rekan kami Jamie dan juga Aksan. Silakan bisa disampaikan langsung dengan bahasa Indonesia, nanti saya coba akan translate ke bahasa Inggris, dan kalau misalkan ada yang menyampaikan langsung dengan bahasa Inggris juga dipersilahkan. Bisa langsung diangkat raise hands-nya atau bisa open mic-nya langsung bisa bicara. Yap.
Ya, saya tanya Pak.
Silakan Pak.
Pakai bahasa Indonesia aja ya, biar nggak
Silakan Pak.
salah persepsi. Bagaimana mengidentifikasi NRW, baik itu misalnya physical losses, administrasi losses, metering, prometer, and tempering. Ini berapa persen, ini berapa persen, ini berapa persen, itu pendekatannya seperti apa?
Oke, ini Bapak dari mana ya?
Saya Irawan dari Jakarta, Pak.
Okay, makasih Pak Irawan. Okay, so I would like to translate Akshay. Actually, maybe this is a bit repetitive and related to the first sessions, but I believe you can answer it about the and non-revenue water, which is how we can identify all those risks, including like the physical losses, timerings, whatever that, how we can help with our solutions the users to identify and to approach the resolutions for it.
So as I mentioned that the more number of data points, the more you can identify NRW levels. So for example, if you have a distribution zone, okay, you first of all you create DMS, district metered areas. That is the most important thing. You need to isolate your areas, district metered areas. If it is having cross connections, just cut down those cross connections, and every DMA should be isolated from each other. You can have isolation valves in between, but it should be isolated. Then in that particular network, how much amount of water is entering into that network is most important. So any pipe which is uh, uh, delivering water into that DMA, you should know the flow. For that, you need to have a flow meter on that particular pipe, okay, and not the pipe which is in at the tank. A pipe which is entering into the DMA should have a flow meter. That is the second point. And the third point will be pressure transmitters. So minimum number of pressure transmitters for a DMA should be 3. Even with less we can work, but for accurate data, you should have minimum 3 number of pressure transmitters. One should be at the weakest or the critical point, we will say, where the pressure is very critical. The second point can be where the pressure is very high, and the third point can be the longest or the farthest point. Okay, so this is the third point. With help of all of these 3 pressure transmitters and the flow meter in your pipe, you can identify where leakages are happening with help of calibrator tool inside WaterGems. If you have digital twin like WaterSight, there are other tools in that where you can identify the same leakage real time. So more the number of data points, more accurate your results will be. But yeah, this is the minimum requirement, that you first isolate your model, or the area, the district metered area, install pressure transmitters, install that flow meter, and then you will find the results.
Okay.
Hope that answers the question.
Thanks Akshay. Jadi Pak Irawan,
Oke.
pendekatannya adalah Bapak perlu ada localized modeling sebenarnya dari Bapak.
Ya.
Jadi
Ya,
dengan tambahan data points ya, mungkin yang sebutkan tadi pressure transmittal, dan demikian juga dengan flow meter, informasi yang bisa kita pakai untuk input analisis di open flows. Jadi ya kira-kira semoga menjawab Pak, atau ada hal lain yang
Yes.
mau di
We have many district meter area, and
Okay.
we operated by with use the PRV, pressure reducing valve, and to maintain the pressure in critical point is always the same. Always can distribute it to the customer.
Okay.
We have identified minimum net flow, yeah, maybe you know. For the first parameter for liquid minimum net flow. We take data from flow meter about in 0.0 until 0.4 EM, and the result is not like that.
Okay.
It's too high. Too high non-revenue water in this area, so we confuse about the to analysis data for minimum net flow, like that.
Okay. So I would also suggest you 2-3 more things that you can do in that network. I mean, in your model is you can also validate the C value of your pipes. If it is very new, it is not required to check. But if the network is old, you also do the field test for C value of the pipes. If those are old pipes, you need to check the C value, and that will also impact the results a lot. Because the C value goes on reducing for old pipes. So that also impacts the network a lot. And if it is under pressure, suppose I don't think it is under pressure, but if it is under pressure, you also check the pump curve, the current pump curve, how it is functioning. For that, you will have to do pump tests. So yeah, there are multiple parameters. So yeah, you will have to check all those parameters. It is not an easy task, I know, but yeah, some place it will match. The results will match definitely.
Alright, thank you Akshay. Pak Irawan, mungkin kalau ada hal yang nanti belum clear, bisa nanti kita engage setelah sesi nanti dengan melalui via Bu Nesi. Makasih pertanyaannya Pak.
Thank you.
Okay, the next questions Pak Wawan, silakan Pak Wawan.
Terima kasih Pak. Ada 3 pertanyaan Pak.
Oke.
Yang pertama, bagaimana cara mengetahui model itu sudah terkalibrasi dengan baik?
Oke.
Yang kedua, apa indikator keberhasilan dari kalibrasi model hidrolik tersebut? Yang ketiga itu, bagaimana Darwin Calibrator ini bisa membantu mengurangi error di simulasi?
Oke.
Terakhir mungkin Pak, boleh nggak kami minta file WTG-nya supaya kami bisa mempelajari setelah ini yang tadi dipaparkan itu Pak?
Oke.
File
Terima kasih.
Terima kasih Pak.
Terima kasih Pak Wawan. So the question is actually, first is how do we can make sure the models calibrated properly? Okay, and then what is the indicator that showing in the Darwin calibrator that our calibration process is okay. And then that's related to this calibrator as well. What else point that we need to what else point that help or functionality from Darwin calibrator to reduce or diminish the error for our calibration process? And then the last part, I think Bu Menesi can support for sharing the presentations better to the users. Yeah.
Yeah,
File
thank
WTG
you, Junius.
file
So the
Yeah, go ahead,
okay.
actually.
Yeah, so calibration is a difficult process, no doubt about it, and it's a continuous process. Means if you are doing calibration, it is not a one-day task. You will achieve some results, but again, there will be some changes in the field, some changes in the pressure, data. The quality of data also matters a lot. The pressure that has been checked at the field also matters a lot. And we have seen in the video, right? I'll just go back to that video. Yeah, this one. So whenever you are doing or using this calibrator, once you are done with all your trials and whatever data that you are getting, at the end you can check with the chart options. You can add your this scenario. You can also add that in the final result. Now once you're done with the calibration, now you will see this, the dotted dots are basically the observed data. This is the data that your model, once it is running, it was giving. But after you run the model with the emitter coefficients that you have got from the Darwin calibrator, now you will see this is the actual flow that is happening or occurring in the model. So this is a continuous process for whatever observed data that has been entered right now in the model. This is the result. But after some time, after a week's time, or maybe some hours time, the pressures will be different, and you may find after few days time, or maybe when the season changes, like in the rainy season, this data will be different. In summer season, this data will be different, and so is the functioning of this model will be different. Also, with this, not just Darwin calibrator, you can also run PDD, pressure dependent demands. There is an option to run in the model. You can test your model with that as well. It gives you more realistic results. Means Darwin calibrator is one of the thing, but PDD also you can explore and run your model with PDD. It will give you more realistic pressures at the endpoints or at the consumer ends. But yeah, calibration is a continuous process. You need to keep calibrating your models. After you calibrate, you can create such graphs. Um, Sorry, Juan, Junius, can you just
Yeah.
repeat the second question?
Yeah, I mean, when you're saying that we need to continuously doing the calibrations, when we can get the indications that okay, our calibration is good enough, the result is
Never.
reliable enough. So
The
that's
the answer is never. So
okay.
that is what it is, a continuous process. Uh, one day it will match, one day it will not match, because the data keeps on changing that is coming to you. So it's a continuous process. Like it's a continuous process. I don't have any other answer for that. Yeah.
We can provide more informations, maybe the case study and the scenario that happening with the reference users later to Pak Wawan. So we can take up that
Definitely.
after these sessions. Jadi Pak Wawan, ada proses di kalibrasi ini adalah proses yang akan terus menerus yang akan dicek dengan aktual di lapangan ya. Ya, jadi mungkin detailnya, referensinya, mungkin best practice-nya dari usernya kita yang lain nanti kita bisa share ke Pak Wawan setelah ini untuk bisa jadi referensi. best
Boleh
practice.
satu lagi, Pak.
Yep.
Pengaruh posisi valves di lapangan yang tidak sesuai terhadap simulasi itu seperti apa, Pak?
Okay. So one additional questions,
Yeah.
Akshay. So what is the effect or influence of the misalignments of pumps locations in this analysis? Is there something that influenced the result, or how it would be the pump locations, elevations,
Pump
everything?
location.
Valve. Sorry, valve.
Okay. No, it won't affect much. Because see, valve is something. It won't affect much of your hydraulic analysis, but it will definitely affect your operational part of your network. Valves, you can just keep on adding the minor losses that the valves will have on your model, but it won't affect your results that much. Okay. But if there is operation that you want to bring into calibration, if you're throttling the valve for maybe 15 minutes, 20 minutes time, that you are bringing into your model, into your hydraulic analysis, that will definitely affect your pressures. Okay. But generally, when we do hydraulic analysis, we do not use the throttling of valve much. We use that in transient analysis. We compute that for transient analysis, but not for hydraulic analysis. Valves will affect your operational part, and that you can test with criticality tool. So criticality tool, you can do segmentation in that, how many number of consumers are getting affected with which valve, all those things you can do in criticality analysis.
Okay, thank you, Akshay. Jadi Pak Wawan nanti detailnya sebenarnya detailnya bahwa valve tidak begitu berpengaruh, tapi pada critical analysis nanti itu sangat dibutuhkan. Detailnya nanti kita akan follow up ke Pak Wawan setelah meetings ini. Kita coba kasih kesempatan ke Pak Rido Satria. Silakan Pak.
Yeah, thank you so much. I think I want to ask directly. So,
Yeah, sure. Go ahead, Pak. Feel free.
I'm Rido from Perumda Air Minum Jaya, PDAM Jakarta, and then I curious about these things, water jumps and open flow. Actually, about the simulation, how many relative errors number during we create the simulation? So like different gap between the result from application and then actual at the project site is the first. And then second, how do we you previously mentioned about the energy consumption. Could we understand or know how many energy consumption that we use during the simulation at Bentley or OpenFlow or in WaterGems itself? I think that's all. Thank you.
Sorry, sir, can you just repeat the first question? The gap, I did not understand the gap between.
The numbers between that we create the simulation and then actual at the project site. Is there any like if we create the simulation and then the result 2 liter per second, but or the pressure 2 bar.
Okay.
Yeah.
Okay.
And then actually is
So,
difference.
for that, we need to go into the formula that is being used in WaterGems. There are 4 different formulas: Darcy-Weisbach formula, there is Hazen-Williams formula, there is Manning's formula, and there is modified Hazen-Williams formula. So we need to study the formula for that. Hazen-Williams formula mentions some amount of plus or minus. So I don't remember the exact value, but yeah, whatever values that you have input, exact computation will be done by the software and given as an output, but with help of Hazen-Williams formula. Now we need to study the Hazen-Williams formula and its percentage of error. Same error will be there. whatever is the percentage in the formula, the same percentage will be there with your model and on ground. Okay, first thing.
Okay.
Second is about energy consumption.
Yeah.
So whatever model you make, if it has got pumps, you can means for any large network, you can do the energy consumption, not an issue. Does that answer the question? Your second question?
Uh, basically, I want to ask about the information about the energy consumption during we create the simulation. Is that really we can get from our simulation using water gems?
Yeah.
So, okay,
Yes.
okay. So
Yeah.
we put some specification of our pumps and then
Correct.
the capacity itself. So
Yes.
directly during we got the simulation, so we get the information about the energy consumption. Yes.
Correct.
Okay. Okay. Clear.
Yes.
Thank you.
The efficiency is very important. Efficiency, whatever is the current efficiency of the pump, according to that, the energy consumption will be calculated.
Yeah, because during the operational, I think we accept for all of PDIM really concerned about the energy consumption,
Correct.
especially about the electrical cost. So
Correct.
we need to minimize the cost and then also, but still optimum to giving the services to our customer. Okay, thank you.
Correct.
Sir. Yeah.
Thank you.
Thank you, Pak Rido. Okay, thank you, Aksan. Looking to the time you have, masih kita coba buka satu pertanyaan lagi. Kalau masih ada, Bapak Ibu silakan. Satu pertanyaan lagi. Oke. Kalau tidak ada untuk saat ini, saya kira kami sangat terbuka untuk bisa menerima follow up pertanyaan setelah sesi ini, bisa nanti disampaikan langsung melalui Bu Nesi atau ke email Akshay dan Jamie Hao. Dengan demikian saya kembalikan lagi kepada Bu Nesi. Silakan Bu Nesi.
Terima kasih Pak Junius. Thank you Aksai. Terima kasih yang terhormat Bapak dan Ibu. Ada beberapa hal yang ingin saya sampaikan. Yang pertama terkait e-certificate. E-certificate nanti akan kami bagikan direct via email. Yang kedua, webinar terkait water, insya Allah akan kita selenggarakan secara berkelanjutan. Jadi mohon untuk tetap stay di WhatsApp group, karena nanti rekaman materi atau sharing link-link yang penting atau modul dan lain-lain akan di-share via WhatsApp group water. Terima kasih kepada peserta yang tetap setia bersama kami dari mulai webinar part 1 sampai dengan 3 hari ini. Bagi peserta yang menginginkan diskusi lebih detail terkait masalah open flows water, kami sangat terbuka untuk pertanyaan-pertanyaan maupun kita bisa arrange meeting private langsung dengan perusahaan Bapak dan Ibu. Dan sebagai bentuk apresiasi kami kepada Bapak dan Ibu hadirin peserta webinar, kami memberikan harga spesial diskon khusus untuk open flow water sangat spesial sebesar 30%, batas booking sampai dengan 22 Mei 2026. Terima kasih yang sebesar-besarnya kepada seluruh peserta atas partisipasi dan pertanyaan yang telah disampaikan. Atas nama Kurnia Handasa Nevada, saya mohon maaf apabila ada hal-hal yang kurang berkenan. Semoga acara webinar ini dapat menambah wawasan dan memberikan manfaat bagi kita semua. Thank you so much, Aksai, Jamie, Pak Junius. Terima kasih semuanya. Sampai jumpa di webinar kita yang akan datang. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you semua.
Thank you.
Terima kasih.
Thank
Thank you so
you.
much, Bu Nesi.
Thank
Thank
you.
you so much,
Terima
Bu Nesi. Thank you so much, Jamie.
kasih.
Thank you so much,
Thank you,
everyone.
everyone.
Bye-bye.
Thank you very much.
Thank you. Thank you.
Thank you.
Thank you. Thank you, Bu.